It's very difficult to change topic and so probably there was some confusion. Somebody else also taught a little bit of this topic, but I was told to teach this topic. So could you? Is it okay that I proceed with this? Periodic table, periodic properties. Maybe you find a little bit difference in way of treatment of the subject. That can be. Maybe I may look into certain aspects which have not been dealt. Okay. So this was actually syllabus given to me. Topics which I have to cover. So basically, why is it required? Why is it required that a periodic table is made? It's a tedious job to remember all the things, right? But have you just imagined? Had it not been there, it would have been even more tedious to remember all the properties of the elements, all the chemical, physical, and chemical properties. So basically, I mean, there are many more, but let us say 114 elements. But so there are 114 elements on the board, and as a chemist, you have to learn the physical properties, chemical properties, different numbers, boiling point, melting point of every element, and it would have been a huge task. So, since a long time, it's not that Mendeleev all of a sudden thought of this. By the way, Mendeleev is considered to be the greatest scientist ever, even in today's world in Russia. Okay, because he had done almost an impossible things possible, and yeah. Right. So basically, what was the need? The need was that it is impossible to remember, it is impossible to expertise or master the properties of such a huge number of elements which have been discovered. So, even before Mendeleev, people were trying to arrange these elements in such a way so that if we remember certain properties, we will be able to predict the other properties of the same similar type of elements. So basically, that is the reason, or that is the impetus. Yeah, okay.
आपका फोटो आपका नहीं आ रहा सर, आप नहीं आ रहे थे. आप नहीं आ रहे थे कैमरे में, उधर चले गए थे ना सर, कैमरे की रेंज से.
बोल सकते हैं ना. So the first one which historically is noted due to I don't know Gogarian, Johannes Gogarian, how it's pronounced, I don't know. So he gave a law of triads. So what his way of arranging the elements was? Suppose now we know what group, no? So suppose you take three elements, okay, which in modern periodic table appears in the group, and you find them, arrange them in terms of atomic number. The middle one is supposed to get an average of the two side elements. So suppose lithium is having an atomic, not number, atomic weight of 7, and potassium is having say 40 or 39, whatever it is. So this guy, sodium, who lies in between, is expected to or will have the atomic weight of average of 2. So that was the basis of the arrangement, and that's how it was done. Next. Okay. So after this law of triads came the law of octave. Now this guy was more fascinated with music, so he told that atomic weight of the 8th element. That time this this Nobel gas or inner gas. They were not considered in counting. So if you are arranging the elements in terms of their atomic weights, so excluding the novel elements in the modern periodic table, as a function of their increasing atomic weights, okay, then the eighth element will uh, uh, then the first element of the series will be having similar properties as as the eighth element. See why this eighth element is coming? Because they are excluding the noble gas. That time the idea was not there. I mean, now with the background of atomic structure and electronic configuration, you can easily understand that these two elements, which have the same properties, will say, okay, they lie in the same group. You already must have been knowing it. Have the same property because they have the same valence shell configuration. It is 6 or something like that. So, what he says that atomic weight of the eighth element arranged as an increasing atomic weight repeats properties of the first element in the series. So based on electron configuration, the second and third periods, later on we will describe the periods and groups. It may be understood why such repetition occurs every ninth element after the normal gas configuration. So because of the common valence electronic configuration, that is NH2 Now this chain is valid up to atomic weight of 40 calcium. So sodium, magnesium, aluminum, they are still working on atomic weight, not atomic number. Remember. So sodium, magnesium, aluminum, if you just go on arranging them with, as an increasing function of atomic weights, you will again after argon, you will again have potassium. So that's how the repetition works, and he described it as law of octaves. Now. After that, several other modifications came which are not so important, but which straight away try to look into what Dimitri and Lutherman also at the same time did. So, from these two previous work, they could conclude that elements arranged in terms of their increasing atomic weight in rows and in certain rows and columns, so that so that elements with similar and physical and chemical properties fall in the same column or groups. Okay. So what they basically try to do from the previous work and their own understanding of the properties, that if you go on increasing the elements, increasing atomic weight in terms of certain rows and column pattern, okay, matrix, then you will get that property that elements falling in the same column will have similar properties. However, in his case, D and D three block elements are clubbed together. Next, please. Okay. So, what was the success of this Mendeleev experiment? Elements could have been given independent position. Law of octaves and law of bands could not generalize the positions of the element, but now they could actually give all the elements. Not all elements, there were some ambiguities, but I'll come to that. Not only that, when arranging systematically or in function of increasing atomic weight, they found that some of the elements, some of the columns or some of the rows, some of the places were left pattern because they could not have any element which can fit in a particular column or particular row. So they could predict that definitely when my trend is getting trend is not following, so there are certain vacancies in the table. So there must be some unknown elements which are going to be discovered later on, and they predicted such elements, such as putting some prefix such as eka silicon, that they all were known that time. Not only that, they could very precisely, get to calculate the atomic weight. Remember, that time atomic structure, atomic electronic configuration were not known very clearly, and atomic weight they could calculate, assuming the valency into equivalent weight. And for valency, he used the group number. So for large number of elements, you could very accurately calculate the atomic weight of the elements. So eventually, earlier published atomic weights of certain elements, which were based on laws of chemical combination, they were corrected. But then there were certain limitations of this table as well. What are the limitations? They could not conclude about the position of hydrogen, and isotopes have different weights. Okay, so but they have the same properties because property is determined by some other thing. Okay, it is basically the atomic number or electronic valence electron. Okay, fine. So that is chemical property. Yeah. So they were forcefully kept in the same place. That explanation could not be given. Even the lanthanides and actinides, he was inconclusive about their position. Then transition metals and non-metals, they belong to the two different subgroups, and they were bundled together. Okay, and then elements with different atomic weight were jointly put in the same group. And anomalous position of certain elements like cobalt, nickel, iron, they were put in the same place, iron, nickel. So these are the limitations of the Mendeleev's table. Now, in between came a very, what to say, one of the greatest scientists. Unfortunately, this guy, because of some rule in America, all young guys have to join army, and he died in a battlefield. In fact, after his death, otherwise he would have got surely a Nobel Prize. So mostly, he was working on the X-ray pattern of certain elements, and he found that when the square root of this frequency was plotted against atomic weight and atomic number gave a much better linearity, and he could get a very good relation with atomic number given by frequency, square root of frequency. Square root of frequency equal to A into Z minus B. Now, where A and B are constants. Now, since you have already learned the atomic structure, you will appreciate the X-ray is coming because some, say, in, what to say, into. So, it is when electron is coming from into to N1, okay. So, you get Hg, right? So, this is the difference in the energy of the two states, and this energy difference is again given by Z square into 1 by N1 square plus minus 1 by N2 square, right? Am I right? So, obviously, if you leave these all these things, so you will get a relation that Z square is proportional to mu, or Z is proportional to root mu. So you basically, without knowing the atomic structure, now it's easy to derive. Without knowing the atomic structure, we could conclude that that is a relation, and then we pronounced that atomic number. Atomic number is more fundamental property of elements rather than atomic weight. So he actually proposed from there onwards that it should be that element should be arranged in order of an increasing atomic number rather than atomic weights for periodic classification of elements. Next. So this is a glimpse of what Mendeleev's periodic table. It's in your book only. Next. So therefore, atomic number is no fundamental property of that atomic weight. I have already told. And properties of elements are therefore repetitive of the atomic number, not atomic weight. So explanation, disability, physical and chemical properties of elements belonging to the same group is due to Similarity in financial approach, configuration as already we have discussed. Just a brief note, it's also given in your CIT book, 11 comes happening. Elements after uranium, they are called trans-uranium elements and they are named in a very, yes, fashion. Till the scientists conclude about the name, Indian University, the name is given as UNNIL 0 to 9 IUL. So 0 to 9 is given as nil, kun, bi, tri, quad, like that. So suppose an element is discovered which has an atomic number of 106. So how will it be named? It will be named. Please, excellent. Okay, so this is just a passing note. Next, please. So, how does the period table looks like into the identities? My Excel sheet. So, maybe we will find more decorated periodic table just to avoid copyright. I have just put this, but you will get much more information on in a periodic. We will come back and forth with for this. Explain. So, at a glance, what did you see? There are certain rows and certain colors. मैट्रिक्स के माफिक है ना लूडो लूडो का जो ये होता है सो या दाबा सर चेस का जो जैसे बोर्ड होता है वैसा होता है सो दिस रोज आर कॉल्ड पीरियड्स एंड द कलम्स आर कॉल्ड ग्रुप्स फाइन so horizontal rows are the periodic are called periodic table. The first one is the shortest. You can see only two elements are there. What are the two elements? Hydrogen and helium. Very good. So the next two periods have 8 elements. They are called short periods with 8 elements each. Then fourth and fifth, they were long periods with 18 elements, which accommodates the transition elements. And sixth period is the longest, which has 32 elements. That also accommodates 14 elements to set of 14 elements. But yes.
Isn't the seventh period complete?
No. The site is incomplete. No.
Sir, what is lanthanide and actinide?
Yeah, actinides are there.
So what are
They are elements. They have the same property as the third group. I will come to them. And they are bunched together in the sixth and seventh element. Only. Tell me what was the basis of the arranging of the elements? Characteristic. आपने समझा नहीं? आपने समझा होता तो क्वेश्चन नहीं पूछता. And when I counter question, you just make question. You try to understand. The logic behind making the periodic table was classification according to properties. Now these properties of actinides and the properties of the lanthanides elements are very close to each other. So they must be put in the same group, and their characteristic is very similar to lanthanum. That's how the name came, na? So they are put in the third group itself. And according to the elementary configuration, they are put in the sixth level. Because we will learn how to select the group or period according to the elementary configuration. What are numbers? Okay, similar activities. But they have the same property as group number 3. समझे? Clear ना? Okay. सिक्स पीरियड में आपका जो है 2n² is the maximum number of ये that electrons that can be accommodated. तो कितना होता है? मतलब after accommodating 32, you are left with nothing. But when it comes to 7, you still have orbitals available. Okay, which are incomplete. So, but there are not elements which you will put. That's why it is incomplete. Got it? Okay. Lanthanides and actinides, series with 14 elements, each forming inner transition elements. Why they are called inner transition? What is transition? We will come to that. Resembles the third group elements in the sixth and seventh period. Okay. So these are the lanthanides and actinides for your reference. Next. Now, vital currents in the periodic table are called groups. So group 1 and 2 are very reactive because they have 1 and 2 electrons in the outermost and where they can be easily left out from the atoms, creating ions and cations. So they are very reactive and they are, I mean, when elements in the group 1 is called alkali element, alkali metal element, and in 2 are called alkaline earth metal. Group 1 it is alkali metal, group 2 is alkali earth metal. So what is the difference in electronic configuration? One has the configuration of NH2, the one NS1, another one has configuration of NS2. Okay. Now just from predictive nature, will come what is the trend and all. If it is possible to complete the entire thing because it's a long chapter itself. Which one will have higher melting point? Alkali metal or alkaline earth metal? With logic. Alkaline earth metal. Why?
They have more complete structure.
किससे? तो उसके साथ मेल्टिंग पॉइंट हायर होगा कि लोअर होगा? Alkaline earth metal का higher होगा. Answer is not clear. It's basically because of the number of more the number of valence electron, more will be the cohesive force, and more the distance, less will be the cohesive force. As simple as Coulomb's law का application सब जगह में.
Because 2 electrons in flying cells, so where energy is required to drop a force, where energy is the
Yes, sir. Yes, sir. So that's the logic. So alkali metals are usually having lower melting point than alkaline earth metal. Okay. So then we have group 3 to 12, and these are called transition metals. Okay. Here we will come later on. Elements are having the d orbitals with electrons. Further, we have group 13 to 17, which are metals, non-metals, and metalloids. I have already talked about metals, non-metals, and metalloids in previous classes. And group 18, which has the complete electronic configuration. Any confusion? Any confusion about the subject? Hello? Any confusion about the subject?
नहीं सर, उसको थोड़ा जल्दी जाना है ना, तो मुझसे कह रहा था उसको जल्दी जाना है.
So I will not go into details of this metals, non-metals. आगे चल सकते हैं. Next slide. We have to cover a lot. So elements resembling the properties of metals and non-metals both are called semimetals or metalloids. I mean there is a difference between semimetals and metalloids. I am not going into that difference. But these are the elements in the periodic table. So we will go to the S block element. What are the S block elements? The group 1 and 2 with last electron. See, the last electron where it goes, that determines what kind of element it is. Am I clear? So group 1 and 2 with last electron going into the S orbital. So alkali metal with NS1 and alkaline earth metal with NS2 occupies group 1 and 2. And their characteristics are, I have already told, they are reactive. Never found in pure form. Almost always you found in oxide or some compound form. They are soft, low boiling point and melting point. Low boiling point and melting point because they have a less number of valence electrons to hold together. Okay? Ionization energy is low because if they lose electrons, they acquire the most stable inert gas configuration. Valid, you got which subject you are talking about? This one. Fine. So then they have a characteristic flame color. All the alkaline metals and alkali earth metals, they have very specific flame color, and just by seeing the flame colors, we can recognize which metal is there. Why this is happening? Because when you are heating it, the transition occurs, electronic transition, and you can see specific color for that. Form cycle compounds with the exception of lithium and beryllium. Clear? आपने पूछा नहीं लिथियम और बेरिलियम क्यों नहीं पता था? बोले वो साहब बोला मान लिया. The greatest problem of our students is they are very much loyal in terms of this. सर ने जो बोला सिर्फ मान लिया. They never contradict. आपको contradict करना पड़ेगा कि आप ज़्यादा समझ नहीं आया. See, इसका साइज बहुत छोटा होता है and it's very difficult to perturb the electronic cloud. There's a sub-rule is called Fajans rule that gives you which to which extent it will be ionic or covalent. तो साइज छोटा होगा, so more covalency will be so more covalency will be there rather than ionic. So because of the small size of lithium and A, they form this. Its ionization potential is extremely high, so you cannot form a pure cation. I mean, you can, of course, ionic compounds are there. Everything is possible, but the possibility is this. Then we come for p block elements. 13 to 18 group number, they have the last electron going to the p orbital. See which orbit? You have already learned the atom structure, right? So in S group, last electron is going to the S orbital. In the p block, the last electron is going to the p orbital. So 13 to 18, the last electron is going to the p orbital. The configuration of p orbital is NS2 NP1 to 6. So group which में p orbital penultimate cell में p orbital रह सकते हैं, f orbital रह सकते हैं, वो अलग. So group 18 belongs to the noble gas family with configuration of NS2 NP6 with very low reactivity and high ionization potential. So p compact elements mostly form covalent compounds. Okay. Group 17, just before the inert gas, they form the halogen family. And group 16 forms the chalcogens. Both the family of elements, that's chalcogen and halogens, they are highly reactive and have very high electron affinity because they are on the right hand side. Now, if they can acquire one electron, they will be having an inert gas configuration, a stable one. So they want stability by gaining electrons. So they are very reactive. Left hand side is very reactive because they want to lose one electron and get to the inert gas configuration, very stable configuration. Right hand side, they also want to get one electron and go to the next inert gas configuration, very stable.
Halogens are alkaline react very aggressively, right?
Huh?
Halogens are alkaline react very aggressively.
Halogens
And alkaline.
and alkaline. Huh.
They react very aggressively.
Huh. The reason I told you, no? Because they want to get the S and P block together forms the representative or main group elements. So when we say these terms, main group elements, I didn't get your question correctly. You can talk about that one because so main group or representative elements किसको बोला जाता है? S and P. Okay, so they are called the main group elements or the representative elements. And P block elements, with exception of inert gases, are called representative elements. Inert gas is not a representative element. I just remember those terms. It will be useful very sometimes when down the line. So representative elements have incomplete outermost cell. What is the requirement of a representative element? It has to have an incomplete outermost cell. Valence electrons less than 8, but complete inner cell. So those are called representative elements. Clear? So inert gas is inert gas in P block element? Yes, sir. But not a representative. Okay. Inert gas has outermost cells completely filled with electron nucleus. Helium has 1s2. That's the exception. D block element 3 to 12 has the last electron going to the p orbital. General configuration of a p block element is ns 1 to 2. 1 भी हो सकता है, 2 हो सकता है. 1 कब होता है? जब वो हाफ फील्ड और फुल फील्ड का कंफ्यूजन आता है. कॉपर इज वन एग्जांपल. D9 हो जाता है. ns1 होकर D10 हो जाता है ना? So otherwise 2 होता है. तो ns1 और 2 हो सकता है. And n minus 1, the penultimate d orbital will be having an incomplete 1 to 10. Okay. Their characteristics are metals, mostly colored, variable balancing. So they have a variable balancing, so they have very good catalyst. You know catalyst, what is catalyst?
It changes the speed of reaction, either slows it down or fasts it up.
And finally, returns back without participating in the reaction. So they must have a very good bond formation and bond breaking capability. So initially they should make a bond, take part in the reaction, and then break a bond and come out intact. So for that you need a variable balancing. Okay. So that's the magic transition metals can do. Good conductors of heat and electricity forms highly covalent compounds under alloys, often exhibit paramagnetism with the exception of zinc, cadmium, and magnesium. Mercury. Zinc, cadmium, and mercury having retained configuration. Being less active than alkali and alkaline art metals, they exhibit a transition property between S and P block elements. So S block elements are highly reactive, P block elements are less reactive, and the metals, transition metals are reactive, but they lie in between. Paramagnetism means a property related to unpaired number of electrons. That's okay for the time being. But when you have all the electrons paired, you don't have that. It's not the complete answer. In certain materials, we know elements with unpaired electrode, they arrange themselves in certain pattern to form a domain. So that they have their unpaired electrons aligned. Now, when you put electric field, they can align in the direction of the material can align in the direction of the field. So those materials are called, you know, magnetic materials in general we call. But magnetic materials, there are different types of magnetic materials, diamagnetic, diamagnetic. So here paramagnetic, iron is used paramagnetic. Fe2O3 is a paramagnetic oxide. Similarly like that. Okay, so we can immediately understand that zinc, cadmium, mercury, they are D block elements, but not transition elements. Because the condition for transition element is they should have at least one of the d orbitals, incomplete d orbital. Clear? Okay. Next. Transition elements. Elements with incomplete d orbitals, both valence 1 to 2 electron and penultimate 9 to 17 electrons are partly filled. Elements with retained configuration are D block elements but not transition elements. For example, zinc, cadmium, and mercury. A block elements can separate two rows are provided for lanthanides and actinides at the bottom of the long form table with the last electron filling up F orbital. Okay, so why is it called inner transition? It is filling up still inner orbitals. Penultimate still further down. So general configuration of F block element is N minus 2, F1 to 14, N minus 1, 0 to 1, NS2. So the d orbital can have 1 electron or 0 electron, and NS2, that uppermost valence electron, will be NS2. They are not in a transition. What are the characteristics? They are heavy metals with high melting point and boiling point, colored compounds, variable balancing. Actinides are mostly radioactives. Properties of elements in each series are very similar. Chemistry of actinides are more complex than lanthanides. So that is the reason they are clubbed together and put in group 3. Okay. Inner transition elements, last 3 shells are partly filled with balanced shell 2 electrons, penultimate 0 to 1, and last cell that should have incomplete. Okay. F orbitals. Next. So how do you identify electronegative table? What's the position of an element? So final quantum number denotes the period. आपका 6s इलेक्ट्रॉन है या 6p इलेक्ट्रॉन है, that denotes your period in the periodic table. And symbol of the final orbital, like P, S, D, that denotes your block. आपको दो ही चीज चाहिए ना, कौन सा ब्लॉक का है, कौन सा पीरियड में बिठाना है. पीरियड कैसे डिटरमाइन करोगे ना, इट इज द फाइनल क्वांटम नंबर. आप इलेक्ट्रॉनिक कैलकुलेशन करते करते जाओ, लास्ट इलेक्ट्रॉनिक क्वांटम नंबर क्या है, प्रिंसिपल क्वांटम नंबर. That's how the periods are arranged. 1s, 2s, 3s, 4s, 5s, 7s. ठीक है. For s block elements, the number of valence electrons denoted group number. For p block elements, one need to change the number of valence electrons. This is the problem, or this is the easier form that in the modern periodic table we have 1, 2, then accommodating 10 transition elements, so 12, and then you have NP6. So like that formation is there. So for s orbital, you can directly have the number of valence electrons or number of group number that denotes your valence that denotes your group number. But for p block elements, one needs to add. Finally, p block में क्या होता है? NP something होता है ना? 6 maximum NP can be. So उसके साथ 10 ऐड करना पड़ेगा, because 10 positions are taken by the transition elements. Clear? In the modern form of periodic table, transition elements are given separate numbers, 3 to 12. Okay. Can you go back to that slide, sir? Oh, लिखी जा सकते हैं. Yeah, no, the 12. 3 to 12 are transition elements, right? So valence electron of s block elements directly denotes the group number, or vice versa. Group number denotes the valency of the elements. Whereas of p block elements, एल्युमिनियम बैलेंस इलेक्ट्रॉन कितना होता है? 3. उसके साथ आपको 10 ऐड करना पड़ेगा टू गेट द ग्रुप नंबर, और ग्रुप नंबर से 10 सब्ट्रैक्ट करना पड़ेगा टू गेट द वैलेंस इलेक्ट्रॉन और वैलेंसी व्हाटएवर इट इज. नेक्स्ट सेंस सर, थोड़ा जल्दी जल्दी बस. और for p block elements, one needs to add the number of electrons to the valence electron. As similar as that. इसके बाद d का जा रहा है, ठीक है, और a block elements are clubbed together in the third group. The confusion is clear. The position of an element in the periodic table is determined by the principal quantum number n of the last cell getting filled, that is represents the period, and the group is decided by the number of valence electrons. Group wise valence. Now we will go to the group wise classification of elements. Can you? Oh, now remember previous. The elements exhibit limitation of properties down the group because of similar number of valence electrons. I am repeating again and again the key points. There are 4 types of elements in the periodic table: S, P, D, and F, just on the symbol of the last orbital field. Next. So what is the exception? Electronic configuration of hydrogen is 1s1, but it resembles both alkyl metals in group 1 and halogen family in group 17. It can form a cation, I will lose electron and form H plus very easily, acid, or it can take आप alkali metal के साथ आप react करोगे तो सोडियम हाइड्राइड बनेगा तो H minus भी बन सकता है ना? सोडियम हाइड्राइड तो इसका ऑक्सीडेशन से क्या होता है? That's all. So both alkali and in group 1 metal and also halogen family in group 17, and hence they are kept separate. Helium configuration is 1s2 but resembles family of fungal gas due to the complete shell configuration placed in group 18. Group 18 में दूसरों का कितना configuration है? ns2 np6. Only exception is helium, where 1s2 ns2. Now valency we have discussed the other day is the combining power of an element as determined by the number of hydrogen atoms or half the number of oxygen atoms with which an atom of that element combines. Clear? A बहुत ही rough definition है, but it works. So it is the number of hydrogen atoms or half the number of oxygen atoms with which an atom of that element combines. Oxygen valency of an element in the third period. Now, when I am saying oxygen valency, what does it mean? Valency we are defining by the half the number of oxygen atoms with which it combines. One atom. The reference is oxygen. Yeah. Hydrogen valency based on hydrogen. So oxygen valency of an element in the third period in elements increases from 1 to 7 along the period. Sodium का 1, magnesium का 2, aluminum का 3, silicon का 4, phosphorus का 5, इसका 6, इसका 7. Okay. So maximum valency. Remember, chlorine can have valency of 1 also, but maximum valency is 7. Okay. So far description of the periodic table is over in terms of modern arrangements. Clear? Quick question है? Quick question. समझ में आ रहा है? ये तो feedback में कोई बोलेगा कि कुछ चीज समझ में नहीं आया. Anyway, if anybody has any question, that's one they can contact me. That is WhatsApp number, and I am available. कभी-कभी होता है कि ये ग्रुप कोचिंग क्लास में भी होता है, क्वेश्चन पूछना मुश्किल हो जाता है. People are shy. But you can WhatsApp me. No problem. Okay. The variation in chemical and physical properties is in line with the balance and electron configuration that I have already told you, which is why there is a periodic variation around the period, whereas properties are similar around the group. So, why we see a variation along the period? Because there the number of valence electron is changing. The variation in physical and chemical properties is in line with the valence and electron configuration of the elements, which is why there is a periodic variation along the period, whereas properties are similar around the group. मतलब close configuration हो जाने के बाद स्पीड शुरुआत होता है NS1 से. तो NS1 वाला सब एक टाइप का दिखाएगा, NS2 वाला सब एक टाइप का दिखाएगा, because number of valence cells, a valence cell electron is same. Makes sense. Reactivity increases down the group for alkali metals, but decreases down the group for halogen. Have you noticed this? Reactivity increases down the group for alkali metals because the size increases. So size increases, it is easier to lose the outermost electron because the pool is less, because the distance is more. Simple Coulomb's law. Coulomb को बदल के डालते हैं. R is coming in the denominator. So bigger the R, lesser is the magnitude of inner force of attraction. So easier to release the electrons. So that's why it is more reactive. Cesium is more reactive. Okay. Whereas down the group in halogen, it is also becoming bigger, but then the pool is less, so electron affinity gets less. As simple as that. Along the period, reactivity increases from metals initially, and then again falls for the then again increases for the halogen. So the reactivity decreases along the period, and then finally increases for the halogen. Atomic radius, I will not go for the definition. You just find it in Google or in your book how they are defined. So atomic radii is different from covalent bond radii, different from metallic radii. Both covalent and metallic radii are commonly known as atomic radii and is measured by X-ray and spectroscopy methods. Ionic radii is defined as half the distance between two atomist ions and ionic ions. Okay, fine. Apart from these, no. Van der Waals radii is also there. This is regarding the molecules, neutral molecules. Okay. So Van der Waals denotes the one half of the distance between two non-bonded adjacent atoms. Two atoms which are not actually bonded, but they remain in the form of a molecule. So in helium, how do you explain? So Van der Waals radii denotes one half of the distance between two non-bonded adjacent atoms of different molecules in solid state or gaseous state also, especially for non-metals. Now, when we talk about bond, basically two atoms are getting bonded, right? So basically, what we try to say that it's a force of attraction between uh, electron of the neighboring atoms are sharing, sharing, and then they are getting hold by the force of attraction of the nucleus. But not only there is force of attraction between the electron of the atom of the neighboring atom and the nucleus, and vice versa, but also there is a repulsion between two nucleus and two sets of electrons. So even when we are considering isolated atom, there are also not only that nucleus attracts an electron. This is JD nucleus, and there are orbits. So this electron is not only getting attracted by this nucleus, but also getting kicked by electrons who are there. So the net result, actually the net force governs how close the electron will be, or what are the forces, or what are the properties. Okay, like analysis from here. So we call this repulsion, mutual repulsion by the electrons of an atom, as shielding effect, and is given by sigma, and often denoted by Slater's rule. I am not once just have chopped it down. I will not go through that. So effective nuclear charge. So basically, an electron is held by the nucleus with an effective nuclear charge, which is given by Z minus sigma. This is Slater's rule. Basically, what will be the value of sigma for different nuclear configuration? I will not go into the details, but just tell me whether a cation will be having say same element. Cation will be having a smaller size, or neutral atom will be having smaller size, or anion will be having smaller size. Same EA. Smaller size. Why is it so?
Then it uses an electron to get
Yeah, but why is so?
the shell, outer shell disappears.
Their effectivity. This is more scientific way of saying it. Because now the repulsion on the outermost electron has decreased because one electron is moved out. So cationic radius is smaller and anionic radius is bigger than covalent radius. Got it? So what is the force acting on the outermost electron? It is the force governed by attraction of the nucleus minus repulsion of the other electrons. Now, if Z remains same, so the force of attraction for a given electron remains the same. But for a cation, we have already removed one electron. So the repulsion effect of that electron is not there. So repulsion is decreased. That means net effective attraction has increased. So that pulls it closer. So that's why the site gets shaped. Opposite thing happens for the anion. Anion, you have gathered one more electron. So kick is more. Although the ZE is same. Attraction is between ZE and E. And the force of attraction is ZE square by 4 pi epsilon naught R square. That's fixed. But then repulsion increases. Because you have added one more electron and he wants to sit in a very clean and start pushing it. So the net effect of this determines where the electron will sit. Okay. Next slide. All these things are written very clearly there. You can see. So a contrasting situation is offered by isolated species with the same number of electrons but different nuclear charge. J definitely increases with increase in nuclear charge, and hence radius increases in that order. अगर J definitely increase करता है तो radius will decrease. So what are the trends? Radius decreases along the period, especially for elements in the second period, because of increase in the nuclear charge. Okay, I will not explain. Can somebody tell me? Along the period, why radius decreases?
Sir, there are the force getting much larger, but the electron sheet is directly negligible. So the radius getting less.
Shielding given by the electrons in the same shell is bigger.
The nuclear charge is increasing along the period. That is more predominant than the repulsion. Along the period, I'm talking about along the period. So radius decreases along the period, especially for elements of the second period. Because of the increase in the nuclear charge, electrons being in the same shell. They are in the same shell. Along the period, they are in the same shell. Okay, so you are increasing one electron and one proton. That's how you are going, right? So just by increasing one proton, the force of attraction increases considerably. Down the group, however, the radius increases as the principal quantum number, as the number of shell increases, and that supersedes the effect of increasing nuclear charge. The distance. When you are considering elements down the group, then the radius of the outermost electron that increases. So that's why the radius increases. Why? This is different quantum level. You have to calculate the Morse radius, it increases. But in the same period, they are in the same principal quantum number, the same orbit, so the radius is same. Whereas the nuclear charge increases. So along the period, radius decreases, along the group, radius increases. Very good. Shielding effect by inner electrons also increases, that also contributes to the radius increase. Okay. Exceptionally, the atomic radii of inert gas are the largest. Why? Exceptionally, the atomic radii of inert gas are the largest because they don't form a bond. They are not reactive at all. Okay. So the radii of monoatomic inert gases, for example, helium, argon, or whatever it is, are more comparable with the van der Waals radii is higher than the covalent radii. They are not forming any bond. There is no effective attraction between the two atoms. Okay, diatomic, although that they are only just having some kind of van der Waals interaction. For transition elements 3D and 4D, the radius first decreases, scandium to manganese, just like the second period, and then it is constant. Manganese and nickel almost had the same radius, and finally increases copper to zinc from red to red across the period. There is an interplay between the increase in nuclear charge and shielding effect of the N-1 unit. Free electrons are more shielding effect. If you have learned in atomic structure class that d orbitals are much more diffused, yeah, so they cannot shield the nuclear charge more effectively. So basically, this trend, whatever you see, the radius first decreases, then remain constant, and then increases. Okay, so this is because of the two offsets. One is nuclear charge increase current, and d electron they don't screen the nuclear charge effectively. Okay. So D10 concentration of copper even more makes it effective nuclear charge decrease. For inner elements, 5 to 16, radius increases with increasing atomic number due to electronic contraction. Just like d orbital, f orbital is even more diffused. So there is a electronic contraction which arises from the core shielding of N-2 f electrons. Neutron diffused electron. The effect is much more pronounced for the actinide 6F. 5F is more diffuse than 4F orbital. The maximum radii are also exhibited by this deuterium and uranium. Since they contribute only 2 electrons to the melting bond as compared to others which contribute 3. I mean, these are just details only. Down the group, there is an increase in the radius from 4 to 5 group, 4 to 5 period, but the value remains almost constant in the 6th period. The effect is again explained by Einstein contraction due to the embedded orbital and increased nuclear charge. That's why it's very difficult to separate transition and non-transition elements. We have so their size is the same. Their effective charges are the same. So I mean they are very difficult to actually this type of properties depend on charge by radius ratio. So charge and radius ratio that they are very similar and that's why they are very difficult to separate. The effect is not so pronounced for detected and for it. Now we come to the next property. Are you understanding what I am talking about? Feedback में ये नहीं आया ना? Sound में नहीं आया? Length contraction आपने देखा है वहाँ की orbital that is orbital D orbital D orbital. If orbital is not diffuse, so that cannot shield the or shielding is coming from what? Mutual repulsion of the electrons. So shielding effect or mutual repulsion of the electrons if orbital electrons is much less. So that's what happens. The nuclear force of attraction is not screened much. In other cases, when D electrons are there, relatively they are screening the charge and the force of attraction reduces. Here reduction is less. So that's why there is a contraction on the side. And that is called Mainak contraction. It is happening because of the diffused nature of the F orbital and poor shielding of nuclear charge by the F electrons. Now ionization enthalpy, what is that defined? Can somebody define ionization enthalpy?
The energy required to draw up the one electron from the outer portion.
From a neutral gas.
Good ones. The atom has to be in the gaseous state.
Isolated.
बीच सीधा डांट देगा उसको डांट दिया So the amount of energy required to remove an electron from an isolated gaseous atom in its ground state as per this equation. Okay, so this is ionization enthalpy. The removal of most loosely bound electron results in the fast ionization and बाद में बात करते हैं ना, but removal of most loosely bound electron results in fast ionization energy. Second electron removal of second electron results in the second ionization energy, and third electron results in the third ionization energy, and so on. Now, can somebody tell me why second ionization energy is always higher than the first, and third one is even more higher than the second?
Because there is less shielding. When there is a problem, there is a shielding.
Right? Over. So I could get you the concept. Next. So it is more difficult to remove an electron from a cation species with higher positive charge due to increased effective nuclear charge on the shielding effect. Extra stability of the orbital is due to half. Sometimes that is, of course, an anomaly when half filled fulfilled orbitals are. Naturally, we have the higher ionization energy or oxygen. Half filled. It will not allow this half filled configuration to change. But it does not requires very high. Ionization enthalpy of beryllium is more than boron because beryllium is 1s2. Fulfilled S orbital. Boron penetration of S is greater than B. So it is more closely linked to the nucleus. Similarly, ionization energy of nitrogen is more than oxygen. Since nitrogen is 1s2p3 half filled. Okay. So this is basically equation, and this is the trade of ionization enthalpy. So ionization enthalpy increases along a period minimum ionization energy for alkali metal and maximum for the energy is also. In general, ionization energy increases with increase in atomic radius, obviously, because the force of attraction decreases, and increases with decreasing effective nuclear charge, which again depends on nuclear charge and spinning. Obviously. So greater shielding is offered by a completely filled inner shell that adds to the lower ionization energy of the alkali metals. Alkali metals में क्या है? एक तो है completely filled orbital है energy vessel में, and not only that, so basically the shielding is highest for them. So that remains the greater shielding offered by completely filled inner shell adds to the lower ionization energy of the alkali metals. And not only that, energetically, if they lose that electron, they attain that configuration. So that tendency is also there. For transition elements, the ionization energy first increases along the period, scandium to chromium, and then remains almost constant up to copper and finally decreases for 2G. Down the road, the radius increases that decrease the ionization energy or enthalpy, whatever it is. In group 13 and 14, like ionization enthalpy of aluminum and gallium are the same, whereas helium and lead are respectively more than that of ionization enthalpy of helium and T, belonging to the same group. This is again a very important concept. They may be attributed to the ineffective shielding of the nuclear charge by DNA electrons and additional nuclear charge associated with the filling of the DNA information. So we call it inert air effect. That comes to. Just remember the term. That's good enough. Good enough. That's why down the group they only have shows canonic charge of 2, not 4, and like that. Similarly, electron affinity, it is defined as the energy given out upon addition of one electron to the outermost shell of the glacier center in its lowest energy state. The process may be either endothermic or exothermic. Exothermic is opposite. An example. Sir? Exothermic case of glutationic. See, in most cases, it should be endothermic, right? Exothermic. Right, why? Because electron is coming, bond is formed, so some energy will be given out. Okay? Right? In which cases? It becomes. In which cases it becomes endothermic?
Sir, when the balance is 1, when the balance is 1.
ऐसा कुछ भी नहीं. Suppose fluorine. Fluorine का size इतना छोटा है. If you want to bring this thermodynamics science, if heat is given out, it is negative. Heat is given to the system, it is positive. So heat is, because of the small size of fluorine, if you want to add one electron to make it fluoride ion, there is a repulsion between the electrons so high that electronic affinity is positive. There may be other examples also, but most of the cases electronic affinity is negative. That means they are exothermic. Okay. Generally, there is an increase in electron affinity, just like enthalpy from left to right, or the period increase in the effective nuclear charge. There is practically no electron affinity for group 1 and 2 The electron affinity is large for 17 elements on the right hand side of the period and actually positive for inert gas. Suppose inert gas, complete configuration. If you want to add one more electron, it will be positive. Okay. So the electron affinity of oxygen is less than fluorine because of smaller size. I'm not sure about fluorine, but inert gas you can understand that this is close to here. I think fluorine also positive. Okay. But for sure, the example is oxygen. Oxygen electron affinity is less than fluorine because of the repulsion due to small size of fluorine. Down the group, electron affinity decreases with increasing atomic size, but again, oxygen and fluorine have lesser negative values compared to the elements down the group because of the small size. So that's where we end our class. I think this is the last time. I will not go to the this thing. This is just don't copy this file. I will send the PDF file to you. VC cell. This one cell. So don't copy this. So I conclude the class here. Any question? No, sir. Any question from that side? समझ में आया क्या पढ़ा है? हाँ सर, क्वेश्चन नहीं है? उनको क्वेश्चन पूछा था? क्या क्या क्वेश्चन पूछा था मुझे पूछो? इलेक्ट्रॉन क्या? समझ में नहीं आया? मुझे क्वेश्चन समझ में नहीं आया। आंसर तो बताओ, पहले क्वेश्चन बताओ। मैंने एक्सेप्शन बताया ना, ऑक्सीजन, फ्लोरीन, inert gas, and basically they are coming because of the smaller size. The repulsion becomes very high. ये मत कीजिए, I will give you the principal sir PDF file में भेज देंगे।
हाँ सर, मैं आपके पीछे निकाल देता हूँ। मैं सब निकाल दूँगा।
मैं निकाल दूँगा।
You defined atomic number as roughly half of the number of oxygen atoms that it reacts with. Should it be double the number of oxygen atoms it reacts with?
I never defined. I told valency.
For valence.
Yeah. So it is the number of atoms of that element that reacts with half the atoms of oxygen. See, no. Half of the oxygen के साथ कितना एटम ये करता है? मान लो one sodium atom reacts with half atom of oxygen. So it is valency is 1. दो sodium atom reacts with one atom of ये. So I am saying it is the number which shows by which is given by the number of atoms which react with half the number of atoms of oxygen. Clear?
Good evening, sir. I am an Indian and I really appreciate the way you go from the very basic to the very top level, so I can understand everything, everybody at that level. Lecture, thank you.
Hello.